In building a specialized homemade engine ignition ECU for my wood gas to electricity projects, I need to know the correct amount of coil charge time, or dwell, needed for the coil on plug or coil near plug packs that we want to use. This setup can characterize the coil charging profile of just about any 4-wire COP or 4-wire CNP pack, single cylinder, or of the 2-tower wasted spark type. The current test setup here consists of the 4-wire CNP pack to be tested under a sheet metal shield, a small 12-volt wet cell for basic coil saturation testing, a simple homemade variable output linear power supply for checking saturation time changes with voltages below and above about 12.5. There's also a single pole double throw switch that is used to switch between the wet cell and the variable power supply, an Arduino Uno controller to simulate an engine but only providing variable coil charging signals between 1 millisecond and 8 milliseconds, and a simulated RPMs between 100 and 6,000, and finally a digital multimeter to measure the applied voltage. This power supply uses a full wave bridge to rectify the output of a 24-volt transformer, the input of which is controlled by a variac. Here you see 4 times 6800 microfarads of capacitors used to smooth the output. Worst case ripple is about 0.8 of a volt, which translates to about 6% regulation at 13 volts applied. Here you can see the 2-tower 4-wire coil near plug pack that is being tested. This one is from a 1990s era Toyota RAV4. It is connected to the 2 spark plugs that you see in the picture. They are simply screwed into the arc-shaped aluminum plate. Notice the long sleeves that connect the plug wires to the plugs. On the bench, this arrangement can generate a lot of RF noise that can reset the Arduino, and that's why I have the metal shielding in place. Here is version 2 of the Coil Saturation Tester controller. This one is more compact than my first breadboard. It uses a direct wired LCD instead of an I2C LCD in an attempt to reduce the negative effects of RF noise. The 3 little pots control simulated RPM, coil charge time, and LCD brightness. The code is pretty simple. I can add a link to it in the description if anybody is interested. Here's another view of my version 2 Arduino controller. This one shows the Uno down inside the cardboard box. Note the twisted wires coming from the CNP pack and the twisting of the leads coming from the Arduino and going to the LCD. This technique also helps to minimize the negative RF effects on the Arduino. On this system, I have shortened the wires, removed most of the alligator clip leads, and cleaned up the wiring considerably from my version 1 setup. It takes a while for a coil's current to reach its maximum. This amount of time varies a lot from one coil type to another. If we don't apply voltage to the coil for a long enough time, we won't generate the strongest spark that particular coil is capable of. If we keep charging it after it has reached its maximum, we don't get a hotter spark, but we do tend to overheat the coil, which probably will shorten its life. That's why we need to know the exact point in time for a range of possible voltages where the coil has reached its maximum current flow. Here I show a series of coil charging waveforms just to show the effect of varying the coil charge time with a battery voltage of about 12.5. You will see that this particular CNP pack needs about 7 milliseconds to get into saturation when the coil is receiving about 12.5 volts. By performing this testing at voltages as low as about 8 volts, which we might encounter when starting the engine with a weak battery at 30 below, and at voltages as high as about 15, which we might see when the alternator is furiously attempting to charge a low battery. Just for grins, here's my version 1 messy setup. I hope you can see from the foregoing demonstration that it is important to get the coil charging time right when designing your own ECU. and I hope that this video gives you some ideas to use in your own ECU related experiments. If you want more entertainment on this subject, watch part 3, which is the bumpy road to getting from the initial COP test setup that you see in front of you to the much simpler design that was shown during this video.